You know, when you look around, from the fuel that powers our world to the very DNA inside our cells, there's one element that's behind almost everything. It's the master builder, responsible for the incredible diversity of life and all the materials we see. That element is carbon. And today, we're going to figure out how this single element creates so much of our reality.
I mean, just stop and think about that for a second. How can one single element be the foundation for so much variety? It's kind of a mind-blowing question, right? Well, that's the central mystery we are going to unravel right now.
The best way to think about carbon is to imagine it's the universe's ultimate Lego brick. Seriously, it's that one piece you can use to build pretty much anything you can imagine. This incredible skill is why there's a whole branch of science, organic chemistry, that's dedicated to studying the compounds of just this one element.
So, what is carbon's secret? What makes it so special? Well, it all comes down to how it connects with other atoms. See, it's not in a giving or taking. It prefers to share, and this little strategy is what gives it its superpowers.
Okay, the key to all of this is this number, 4. A carbon atom has exactly 4 electrons in its outer shell. We call them valence electrons. And those are the ones that are available to form connections or bonds with other atoms. And as it turns out, 4 is the perfect number for building just about anything. And yeah, there's a fancy name for this ability to form 4 bonds. It's called tetravalency. What it really means is that a single carbon atom can act like a central hub, branching out and connecting in 4 different directions all at once. This creates these incredibly stable three-dimensional structures. Now, to really get why carbon is special, you have to know there are 2 main ways atoms can bond. On one hand, you've got ionic bonds, which are all about giving and taking electrons. But for carbon, giving away 4 electrons or grabbing 4 more, well, that's just way too much work. It takes too much energy. So it chooses option number 2, covalent bonds. It's a strategy of share and share alike. And a covalent bond is basically like a really firm handshake between 2 atoms. By sharing their electrons, both atoms get to feel like their outer shell is complete, and that makes them super stable. These shared bonds are incredibly strong, which is exactly why carbon compounds are so durable and can form the very backbone of life itself. All right, so if being able to form 4 bonds is carbon's first superpower, then its ability to bond with itself is definitely its second. And this is where the real architectural magic starts to happen.
The technical term for this is catenation. It's just a word for this amazing property of self-linking. And believe me, carbon does it better than any other element out there. Why? It's simple, really. Carbon atoms are small, and the bond between 2 carbon atoms is exceptionally strong and stable. This lets them link up to form the skeletons for millions of different molecules.
So with this self-linking power, carbon can basically draw up 3 different kinds of blueprints. It can form these long, straight chains, it can create branches off of those chains, and it can even loop back around on itself to form rings. Just with these 3 simple patterns, you get the foundation for pretty much all organic molecules.
Okay, so we've got the blueprints. Now, let's start building with the simplest stuff there is. It's time to meet the most fundamental family in all of organic chemistry, the hydrocarbons. I mean, the definition is literally right there in the name. Hydro for hydrogen, and carbon for, well, carbon. These are the simplest organic compounds you can make, but don't let that fool you. They form the basis for everything from the natural gas in your stove to the plastics all around us. Now, we can sort these hydrocarbons into 3 main families, and it all comes down to how the carbon atoms are bonded together. You've got alkanes, which only have single bonds. Then there are alkenes, which have at least 1 double bond, and finally alkynes, which have at least 1 triple bond. It might seem like a small difference, but that change in bonding completely changes their properties and how they behave.
And this difference in bonding leads to another key distinction. You could almost call it their personality. We call alkanes saturated because they're holding the maximum number of hydrogen atoms possible. They're stable, kind of reserved. But alkenes and alkynes, they're unsaturated. Those double and triple bonds are like an open invitation, making them much more reactive and, well, ready to mingle chemically.
Okay, so we've been through a lot of theory, but how does this actually affect you? The answer is everywhere. These carbon compounds aren't just some abstract idea in a textbook, they are the literal fabric of your daily life.
Think about it. The methane that might be heating your home, that's the simplest alkane there is. The plastic in your water bottle, that's polyethylene, which is just a long chain of the alkene, ethene. The ethanol in hand sanitizer, and even the soap you use to wash your hands, they're all these elegant structures built by carbon.
Let's just take soap for a second, because it's a perfect example of carbon's clever design. A soap molecule is basically a long carbon chain with two different personalities. One end, the tail, absolutely hates water but loves oil and grease. The other end, the head, loves water. So when you wash your hands, the tails dive into the grime and the heads face out towards the water. They form this little package called a micelle that traps the dirt inside. Then, when you rinse, the water grabs onto those water-loving heads and just pulls the entire package, dirt and all, straight down the drain. It's brilliant.
And this really brings us full circle. From the simplest soap molecule all the way up to the most complex life forms on the planet, carbon is the one common thread. The proteins, the fats, the carbohydrates that make you who you are, they're all built on these incredibly intricate carbon frameworks. It really is the architect of life.
So as we keep learning more about the unbelievable versatility of this one single element, the question really isn't what carbon can build anymore. The real question is, what are we going to choose to build with it next? From brand new medicines to futuristic materials, the possibilities are, well, they're pretty much endless.